Hello and welcome to one of my coding videos where today we are going to talk about evolution. I have made a evolution simulator, and not only am I going to try to explain it, I'm going to go into some details about some of the interesting aspects of what it is that I have made. If you want to go and check it out, run it for yourself, or make tweaks to it, there is a link to my GitHub in the video description, and let's go. So, let's get started by talking about what evolution is. Now, in this video, we aren't going to go into the details of deoxyribose nucleic acid or the molecules or the cells or anything like that, because that's way too complicated. But I do want to answer this question to a reasonable degree in order to be able to give people a standard background whilst watching this video, so that everybody is able to equally understand what it is that I am talking about. Let's say that we have a little creature. And this creature, it wants to be able to move around. Okay, so this little creature has some eyes. Okay, this creature's on land and it wants to be able to move around from like side to side and up and down, all over the place. Okay, in order for that to happen, this creature itself can't just choose to grow legs one day. That's not how it works. It's the same way as that you can't just choose to grow a third arm or to grow another toe. It doesn't work that way. But let's say that our little creature here has a kid. And this kid, through the randomness of the universe, is born with a little stump. And say that kid has a kid, and that kid is born with another stump on the opposite leg. And then say, after some iterations, there's muscle, and this little guy is able to move around. He's able to move these legs back and forth and able to move around. Now, this took lots of time, but you see, time is relative during a simulation, and that's going to be important when we talk about what's next. So, essentially, what evolution is the action of, over time, a ability being developed in order to be able to facilitate a life form being able to be more fit for a scenario that they are in, or habitat that they are in. So, let's get into what this program is. On this program, we have a grid that is made up of squares. In order to be able to understand any of this, we have to first understand the basic rules. Now, the rules of the simulation are simple. There are berries, and we're going to show berries as purple. And there are mites, which we are going to show as green. Okay? Just for those who want to be able to keep track, we'll put some circles over here so that people can... So we have mites and berries. Now, the mites need to eat the berries, okay, in order to be able to live, okay? So let's say that we theoretically have some mites on our screen. Say we have one here, and we have one here, okay? And let's say that we have some berries. If, by random chance, a berry were to spawn next to a mite, such as like this, then that mite is able to eat that berry. Now, by eating one berry, a mite is able to sustain living for an extra day. Okay? By not eating any berries, the mites will start to starve, and they will lose 10 health per day, which is important, so remember that for later on. So, let's say that the mite eats more than one berry, though. Say he eats 2. If the mite eats more than one berry, he has food, and he has some left over, which means that during the reproduction phase of the day, that mite could reproduce, creating another mite, which is its offspring. Now, first thing is that this mite has now created an offspring, okay? And in order to be able to identify offsprings, I wanted to be able to have a clever way to be able to do it, so that it's identifiable when debugging lots of iterations. So, I came up with this very interesting line here, line 124, which basically made it so that every time that a mite reproduces, it is the father's name, or the reproducer's name, plus an A at the end, which means that theoretically you would be able to pinpoint what generation a mite is from. And you could use this in order to be able to trace back what mite it originally originated from, as long as all of your mites have different originating names. So, this makes things extremely easy. So if, say, this one is named, and then this one would be named Calvin A. Okay? And if, say, this one were to reproduce, it would be Calvin AA, which is pretty interesting. So, the thing with berries, though, is that they also want to reproduce, because if they don't, they'll just die out. They don't want to as though they have a consciousness, though. They need to, okay? So, for the berries, essentially, if they grow a certain amount of days, they can reproduce another berry around them in any square, say here, okay? But after a certain amount of days, that is larger than the certain amount of days for reproducing, they will die out, which sort of gives this effect of the berries moving across the screen, except they aren't, because they follow the same code that the mites take, where in their code they get a random number added to the end of their name, which essentially makes it so that if you can pinpoint the name, then you can pinpoint how many iterations it has gone through, or how many generations it is, dependent on how many digits it has and what the first digit is. So if it's 3, 4, 9, then you would know that it is 3 generations in, and that the first berry was named 3. So that makes it so that the berries are able to reproduce. If you take away these two attributes, the simulation will not work, because of the fact that it will make it so that if the mites are not able to produce, they will inevitably starve off unless they are in a situation where the berries are able to reproduce and they are literally everywhere, and you have the statistical likelihood of that they are able to consistently reproduce every time. So, let's get into a little bit more of the nitty-gritty. A couple of interesting rules that I put in for these things is that with berries are not able to reproduce if the berry that it's reproducing wants to be on the same square as the reproducer. This makes it so that there is a statistical likelihood of that a plant will just not be able to reproduce because of circumstances that are outside of the control of the plant. The same goes for mites. And that also, when one of these wants to reproduce, it has to check to make sure that the box that it is attempting to go to, say this one, the reproducing berry wants to go to this box. If this box is occupied by a mite, it can't do that. So it will just not do it. But mites are somewhat spared from this process due to the fact that when this happens, their health doesn't necessarily get as penalized from it. The berries, on the other hand, don't have such a luxury. So one of the interesting things that we saw in early iterations of the game, which still can be showed, is that after a million iterations or so, or however many you want to do, the berries will still be remaining, and they will not take up every square. So when we go and we see this first run, you will see that the berries are numbers and that the mites are letters. If we run, say, 15,000 iterations, which is highly unlikely for mites to be able to survive.
3 hours later.
Okay. So, this is from the last iteration, and essentially what we see is that all that remains is berries, but they have not covered the entire screen. And in the areas where they are occupying, there are these pockets, because essentially every time that a berry plant occupies an area, it wants to be able to reproduce. But if there are other berry plants around, it becomes exponentially harder for it to reproduce, which makes the likelihood of that square to become occupied to be less and less and less and less until it's almost 0%. But it will never reach 0. It will always have a chance to be able to occupy that square whilst the other squares are occupied. This means that the mites are meant for the berries as much as the berries are meant for the mites, which is extremely intriguing. So when asking the question of reproduction of, say, a mite, we're going to be using some numbers, okay? First thing that I kind of wanted to play around with was the idea of health. If you have a mite and it has a health of 100, meaning that it's 100% healthy, okay? Or say, how about 85? A moderately healthy mite, and it wants to reproduce. It took 2 berries, wants to reproduce. What does it do? Well, it reproduces, but it's not guaranteed that this mite that it reproduces to get will have the same health. Because if it had the same health, that doesn't really make any sense. Because it hasn't really done anything to deserve it, you know? So, let's say that it has a plus or minus of 85 of the 85 health that the birthing mite has. Okay, so it could either be 95 or it could be 75. Okay, so if it gets 75, okay, that means it got a pretty bad hand in life, you know? It got sort of dealt a bad hand of not having a good immune system, and it wasn't able to do well during that sort of process in life and whatnot, and it didn't go so well. But let's say that the other side is true. Let's say that's 95. Well, that's pretty good. It means that it was strong, it did really well. See, what you might think is that, oh well, this is a random event. This is something that is pretty normal, but it doesn't seem to really sort of connect to what we're talking about evolution. Well, let's look at it this way. So let's back up, okay, to where we have these two mites, okay? And let's say that mite A, that's what we'll call this one. We'll give it a little A down here so that you can see that. This one will be mite B, okay? So if mite A has 100% health, say first round, this is what it does, okay? Eats two berries, it gets the ability to reproduce, successfully reproduces onto the next square. Then what happens here? Well, if you were to keep the same value, of what we did for everything else, the same code and everything, there's a possibility that, statistically speaking, it could have 110 health. Now you might be thinking, whoa, 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 that's really unfair, you know? The other mites don't have that chance. They might not have that chance. But the thing is that that's the purpose, is that because of randomness, specific mites should be able to do better than other mites. So let's say that we keep going along with the story, and let's say that this mite goes away. He doesn't necessarily make it. This one's surviving on, okay? And this next iteration, it eats two berries, it's able to reproduce. Well, now if we look at it and it reproduces into this square, it has the possibility to be able to get 120 health, okay? Which means that if this keeps going and every single iteration the next birth mite eats two berries right away, it should be able to create super mites that are able to survive for longer. And essentially, there's no cap to this, which means that it can go as long as you want. It can do as much as you want. Theoretically speaking, from this code being added, you could have mites that are able to survive a drought by being able to store more, by having a higher capacity, because they've sort of developed that, by making it so that, let's pull up a wave here. I love Desmos, so let's pull up Desmos, okay? Let's pull up a wave. So let's say that the berries reproduce, and they reproduce, and they reproduce, and they occupy a whole bunch of space, okay? So the super mites are able to really flourish off of this, but they take a lot of the berries That's one of the big things about the supermites, is that they take a lot of the berries because they need them right away. If they don't, the likelihood of them being able to increase again decreases. But then let's say that the berries go away because of this. They go away, they go away, they go away. There's an equilibrium, then they keep going down and down and down and down and down and down. So at this point, the mites that don't have this super ability would die off. Now, typically, in the code that I wrote, we were seeing that around iteration 10 or 11, which is that since they take 10 damage each time, without having another berry, they die around iteration 10 or 11. Now, there are exceptions for some that scrounge up berries and whatnot, where they live on to 16 or whatnot. But if you have a supermite that is able to have the ability to have 200 health or so as their starting value, they would be able to survive from here down through the drought and then up to the next surplus. And by surviving to the next surplus, they have guaranteed their chances of being able to reproduce. Now, it's not 100% guaranteed. It's not like, okay, great, I made it, I'm here. Okay? This mite could be in an absolutely droughted area in the map and still die in this next droughted era. It all depends on likelihood and on randomness. It's all just like dice. And you can't predict a die, and you can't predict this. But what we are working with is the fuzziness of what we can predict will most likely happen. So this is interesting, and that is why in the code I put this comment on line 123, which says accidental mutations supermites, which sort of shows that this is where we had the first contact with mutations, which is really interesting. So let's keep going. Let's see what else we got. Okay. So we have this, and let's first ask ourselves, okay, wait, we're not doing this in sort of, like, how are we storing all of this? Because I think that that's important. Well, the way that we store it is that we take the points of every single living organism on the map. So here, 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 and here. And let's put a couple more of these in here. Okay, so this is such and such point, this is such and such point, and it keeps going through these and it creates these points. So the actual, it's not stored in a specific storage system. It's stored in a system that has these as values. So instead of making it so that we have a bunch of arrays and then an array that goes through those arrays, we have a system where every object has an x and y coordinate, and those values are used as the way to be able to figure out how to be able to work with things. Now, how do we judge the difference between the two? We use the isInstanceOf operator as sort of our working way of being able to figure out this stuff. So we go, well, is this an instance of a mite? And it's like, yeah, it is. So we're like, okay, cool. Then we do this. And then if it goes, oh, is this an instance of a mite? No, no, it's not. Okay, well, is it an instance of a berry? And it's like, yes, yes, it is. That way, you can be able to use different ways to be able to distinguish between different things without requiring the parent class to have all of these extra things added to it. Now, I could show this here for the people who may not understand code that much, where essentially you need to have something that says, okay, all of these other objects that we have these base things, so that we can basically work with them a bit better. It's kind of like how a car and a truck. A car and a truck are very similar. They both have four wheels. They both have a dashboard and a steering wheel and everything, but a truck has a bed and a car doesn't, which means that you could say that you have, say, motorized vehicles as your class, as your base class, and then you have cars and trucks as your sort of child classes. So if you wanted to see the number of wheels, those would both be things of cars and of trucks, and that would be something that would be in the base class. But motorcycles have two wheels, and that way you can be able to sort of distinguish between them. So, but they both all have wheels. So we use the base system in order to be able to figure this stuff out. So we have just the base stuff that we need, like names, x and y coordinates, and this boolean called isDead. So isDead is basically used as a way to be able to remove things from what we call the existence plane. Okay? And if something gets removed from the existence plane, it doesn't exist anymore and it won't be rendered. Okay? Now, I will admit that this causes memory issues, because essentially you're still storing these objects without deleting them. But to be honest, I was trying to get this done, and there's a whole bunch of other bad stuff that I did also. So we'll cover that later. We'll cover that in a bit. Okay. So this has all of these methods in order to be able to deal with this, and then might has all of these methods too. But for all the coders out there, I definitely think that for commenting, that this is something that we should get in the practice of doing more, which is that if you have a variable in the commenting section, you should tell where that variable is being used. Because if you tell where that variable is being used, then it's a lot easier to track down what the problem is with that variable when you have an error. And it makes things just a whole bunch easier. So let's go, if we go over here, back to our example, let's say that we want the mites to be able to survive for quite a bit longer. Well, how do we do that? Well, the way that we do it is to make it so that we add, first of all, our first formal mutation, not one that's accidental. So the way that we do that is that essentially we say, okay, let's give them biases. When they move in a random direction. They're like, okay, I could move here, I could move here, I could move here, I could move here. But that's very random. Okay, that's essentially if you were to plop someone in the middle of field, they were to pick one random direction, and then eventually they get lost and they just kind of start going in circles. What we're basically doing is we're going, okay, you have this need to go in this direction, kind of like a homing pigeon. Okay, so say their need is in this direction. Okay, which means that with their vectors, they're always going to want to move in that direction. And I'll show you what I mean. In our movement class, okay, the original of what it was that we had the x value plus this sort of random value of moving in any direction of any choosing, okay, which is a vector between -1 and 1, which means that since it's an integer, it can only be -1, 0, and 1. 0 means that it doesn't move, -1 means that it moves to the left, and 1 means that it moves to the right. So if you have, down here, if you have the random bias of +1, okay, the random movement of +1, and you have the bias movement of -1, these cancel out. which means that it just doesn't move in that direction. But if your bias is in this direction, that's great, because they add together. Because 1 plus 1 is obviously going to be more than 1, and it's not going to be negative, and it's not going to be 0. So what you can do is you can do some special code to make it so that instead of it jumping forward to space 2, because it's not supposed to do that yet, it stays at 1, okay? Now, let's say that it's 0, though. Well, that means that it still moves in the same direction because of the fact that it just doesn't help, but it also doesn't hinder. But it also means that in the other case of that the bias is 1 and the randomness is 0, it still works. Now this also works on the y-axis, but I wanted to explain it on the x because it kind of just makes a bit more sense. So, essentially, to sum this up, we are making it so that the mites want to move in a direction, essentially sort of giving them this spidey sense of a pull towards a direction that they should go. Now, it doesn't mean that they're always going to go in that direction because of this randomness, okay? But it does mean that they will want to go in this direction. So, say that you have a wanting to go in this direction because the berries are all down here. Now, you see, the mite doesn't know that the berries are down there. The mite doesn't know anything, okay? It is completely oblivious. All it wants to do is to eat berries, okay? But when it does eat 2 berries, say that there's 2 berries down here, okay? But when it does eat 2 berries, it eats them and then it reproduces. Now, that style was successful. It moved down here, it was able to reproduce, so therefore there should be, most likely, more berries in the same direction. So it reproduces. This new mite should have the same bias as the old mite, because if it does, then that means that both of these will reproduce in the same way, and it will grow that part of the gene pool, or it will grow that sort of mutation. Okay, so say that this one starts to move, and it moves in the same direction. Okay, clones the direction that its dad was moving in, and it moves past this. Okay, and so it reproduces when it hits it, and it is able to keep the system going. It's able to make it so that that they're able to reproduce. And if you were to have an abundance of berries in the bottom right hand corner, this would work, and essentially all of your mites would be able to do this. Now, let's say that you were to sort of get to a point where, say, this clump is everything. Going past this point, there's not many berries. Well, if the mites were to be able to reproduce and the next mite were to reproduce and its vector were to be mutated and were to be less, say, maybe just nullified, so that it doesn't really move in a direction so far, that any direction that isn't. So it doesn't have any bias, so it's just going to move in a random direction. It will stay within this area, which means that it kind of just moves in this cloud instead of in a direction. But it will stay within the berries, and it will be able to eat them, which means that that gene should be replicated. But it was only possible because these genes wanted to move down and to the right. And that was only possible because of this one, and so on. Which means that we need to be able to make it so that the genes of the reproduced mites are able to be modified from their parents. So that it's not none, but it's not everything. Now, you'll see what I mean by that. If we go into the code and we go into the mite birth function, we've reused some of the same code in order to create the bias X and bias Y of the reproduced mite, and it has some of the same sort of vector canceling out properties of that. When a negative comes in contact with a positive, it's able to deviate, but if a positive comes in contact with a positive, then it stays the same, and such is the same for a negative, of that it would stay the same. Now, we ran iterations of this and actually found that the mites are likely to survive 3 times longer whilst having this code in, comparative to the mites only having the their parents' code in, basically meaning that their bias is exactly identically the same. So what this means is that in specific situations you could have a situation where the mites move down the coordinate plane and just keep moving and don't care about what's in their way. And you can have mites that travel down and then stop and then just kind of chill in an area for a while. You can also have mites that when they reproduce, they just go out in all different directions, doing all sorts of different things. And that is kind of honestly the beauty of randomness, of that certain things are possible and other things are also possible. And yeah. So the movement is an extremely intriguing idea, and the sort of idea of the mutations can be expanded upon. You could make it so that there are mutations that are essentially percentages, and then once it reaches a certain threshold, it will actually augment the behavior of a mite. And what that does, translated to the real world, is the idea of having dominant and recessive genes and how those genes interact with each other, and to see if certain genes that are in sort of this dominant state are able to affect more change than those that are in a passive state or a recessive state. But what this does also mean is that when you have a program that is like this, every iteration will be different. You could run the same program 5 different times and get completely different results. Now, some results that I got were kind of disturbing. There was this one result that I got in the sort of last part of the coding that I was doing, where the mites had essentially eaten all the berries. Now, typically the way that this was set up was in such a way where there were berries on the outside that were kind of just around so that afterwards they could reproduce. But in this specific example that I was running, that wasn't the case. They were all kind of meshed together with the mites in this sort of weave. And by doing it in such a way like that, and making it so that there was no sort of way of reproduction, the mites and the berries, for the first time, both died out, making it so that the grid reduced to a 1 by 1 square. That was the first time that I saw that in the 7.5 hours that I had been coding at that point. And it was extremely upsetting, but also interesting at the same time, because it was a real showing of what not taking care of a system and what greed can lead to. This is extremely interesting to just look at also, because it means that there are showing of what not taking care of a system and what greed can lead to. This is extremely interesting to just look at also because it means that there are specific setups that you could do that would give you different results. Having the berries meshed with the mites would have a different result than those that would have sort of berries on the outside and mites on the inside, or berries on the inside and mites on the outside, or a sort of cell-like system, or an island-like system, or maybe you have them really far apart. There is no limit to this simulation, except what your imagination is and also what the code says. But essentially, from this point forth, it would just be sort of modifications. Now, someone that is very smart and very insightful said something to me of that this is somewhat of an interpretation of Conway's Game of Life, which I extremely loved that compliment for. And I do somewhat see it now as a sort of take on Conway's Game of Life. Now, Conway's Game of Life, if you don't know what it is one of the most simple zero-player games out there that works at basically the base level because it uses just binary and whatnot, and is extremely elegant. My version is a lot less elegant, but is able to sort of take a lot more creativity to it, and I challenge people to do that. There are specific things that I have done for quality of life also to this, such as making it so that you can pre-program in specific orientations of the mites and berries by putting in a file, and then also making it so that in case your terminal runs out of space, like you're using JGrasp like me, you can have it outputted to a file so that you're able to see it all a lot more clearly. So yeah. So I believe that is all. I'm hoping to do a lot more to expand this, but I do also have a lot of other projects that I am working on. If you have any questions, feel free to leave them in the comments. If enough questions emerge, I may create another video in order to be able to answer those questions and to sort of give an update as to what I've done with this. There is a 3-part full version of the entirety of the process of me creating the program and whatnot, and all of the mistakes and tools that I used along the way. And then there's also a 16 times version where essentially it speeds it through and gets it done in like a half hour. It shrinks down 8 hours into a half hour. And it's pretty cool to watch. I definitely turn the volume down on it though, because it's a little hard to listen to. But yeah. As I said before, go check the GitHub. Thank you.